Hi, my name is Jayesh Lalwani, and I work at Capital One. I'm a lead software engineer in we manage a product called Quantum. And what Quantum is it's a framework built on top of Spark, and it enables people to adopt Spark easily within Capital One. And as part of my job, what I get to do is work with a lot of teams across Capital One to help them adopt Spark. So last year we had one project which was doing a pilot on structured streaming, and I got to work closely with them. And as part of that, we had some learnings. So I wanted to present those learnings in this talk, so people have an idea of what are the common pitfalls or common problems in using structured streaming, and so people can avoid that. So how many people are familiar with Captain Haddock? So this is from a Tintin comic series, and Captain Haddock is like, he gives out a curse when something goes wrong, and usually his curses are very alliterative. And I sort of felt like that when I was playing around with structured streaming, so I sort of used Captain Haddock as my mascot. By the way, how many people are developers here? Like, how many people write code or write code? Because I'll be showing code. So most of the people are. I mean, even if you don't work with code, I think you still gain value out of this talk. So just a brief intro on what is structured streaming. What structured streaming allows you to do is basically get events, and within Spark, those events go into a logically unbounded table. And you can treat that unbounded table as a data frame. And this is something which is really powerful about structured streaming. It basically gives a unified view of data, whether it's streaming or batch. And that is one of the reasons why we started using it, because we had a lot of code which was built around batch, a lot of reusable code, which was built around the idea of data frames. And using structured streaming allowed us to basically reuse that code, because within structured streaming you're operating on data frames. And this is something which is unique about Spark, and what we love about Spark. But once we started using it, we started running into problems. There are like a couple of families of problems. The first family of problem we had is, how do we take data from batch data sources, for example, database or file or MongoDB or whatever, and join it with the streaming data. And Spark does allow you to do that, which is also something which is unique about Spark. But when you look at the confluence of different problems, when they come together, you start running into some challenges. So the first challenge which we run into is that Spark does not push down join predicates. And what that means is that if you're joining, if you have a table which is loaded from a data store, from a file or from a database, and you're filtering on it, what Spark will do is it will push down that filter into the data source, right? So this limits how much data comes into Spark. But if you're joining two tables, Spark will not push down the predicate to the data itself. What it will do is it will load data from both sources and join it in memory, which works great for batch, right? But what happens in streaming is the streaming data frame is usually very small compared to the batch data frame. So imagine you have this process up here, process A, which is creating some batch data and updating state in some sort of data store, could be database or anything. And imagine that has billions of records. And let's say you're getting some events at 100 TPS, right, into your streaming process, which is the process B. So each micro batch will have like 100, 150 records, depending on how frequently you're getting your micro batches. So what you're doing is you're joining a 100 record micro batch with a billion record table. And what happens is for every micro batch, it keeps getting the data into Spark if you don't cache that data frame. Let me show an example of that. So this is my so this is an example. Sorry, not this one. So I have this table. I have this Parquet file called salaries, which has about 24 million records, and it basically has how much salary, monthly salary for about 1 million employees for the last 2 years. So it has 24 months of data for each employee, 1 million employees, so it has 24 million records. And I have a stream which I'm reading where I just get an employee ID. And what I want to do is, as I get employee IDs from the stream, I want to join with the salary table to get and print out what the salaries are. So let me run this. So this is going to run in a minute. In the meantime, I'm going to show you the execution plan. Oops, I made a mistake. Right, for some reason it didn't run. Let me just copy it in. Okay, so on the other side I'm sending a stream. I'm sending one record through the stream. So basically it joins it with the streaming record and gets the data back. And if you look at the query plan, sorry, this is not done. Yeah, so what's happening here is it's basically, you can see it's not pushing any filters down to the Parquet, and it's trying to load all 24 million records into memory to run it. So one way you can solve this problem is by caching your patch database. So what that prevents is, so Spark will load the data from your data store once, and then it will keep it in memory, and when it does the join, it will do an in-memory table scan. But the problem there is that the data might change while your streaming job is running. The streaming is an always-on application, and when you cache it, that data comes into memory and it gets frozen. And if there is some other process running which changes that data, you won't see that in your application, right? So it's like in Spark there is either or. Either you get the whole data back into Spark, into memory at every micro batch, or you get it once and it stays for the life of the application. So the only way to solve this is, there are a couple of ways you can solve this. Not all of them are ideal. So one way you can solve it is by restarting your application itself. Yeah. One way you can do is restart your application on a frequent basis, maybe like a daily basis, depending on how frequently your batch data changes. Usually your batch data is updated by some sort of patch process which runs at a cadence. So what you could do is restart all your streaming applications at that cadence, which is not an ideal thing to do, but that's what we ended up doing. Another thing you can do is, rather than restart your application, you can keep the Spark application on, the streaming application on, but you can just restart the queries that are running inside the application. And I can show you a code sample how you could do that. So here's an example. What are people familiar with streaming query listener? No. Okay. So what streaming query listener is an interface provided by Spark. You implement that interface, and you can register it with Spark. And what that does is Spark sends you events at the end of every micro batch. So it will start this on query progress. It will call on query progress between micro batches. What this allows you to do is, usually most people use this to do some look at some statistics or print some statistics out, or like publish metrics or things like that. But what you could do anything in on query progress. So what we had done is, this is the usual way you do start a streaming query. Basically, this line starts a streaming query. And after that, usually in a Spark application, you will call query.await termination. And that's what keeps your Spark application running while the stream is running. When the query stops, await termination exits. So what we have done is we put that in an infinite loop. So once the query exits, it will go back and start it again. And what we do in the on query progress event is, we check, is it time to refresh our caches, right? If it is time to refresh our caches, then what we do is we go and call unpersist on the cached data frame. So this is the data frame which is cached, and what we do is we call unpersist on it. So this will force Spark to reload the cache next time that data frame is used. And what we do is we go and stop all the active queries. So what will happen is, when you call this stop, this query will stop. It will exit it from await termination and go back and restart the query. So that way the application keeps running and the whole query restarts, and it will refresh the data from the cache. So this is the solution which you can use in 2.2, but 2.3 has another thing called stream-to-stream joins, and this is the preferred option that Databricks recommends. Which is, what they say is, rather than join a streaming source with a batch source, what you can do is that treat both sources as streaming sources. So the process which is updating your batch source should stream an event to your streaming application. So you can have two streaming sources, and then what you can do is you can then do stream-to-stream joins. And then what happens is, if the process which is generating the new data for the batch, instead of that, it should send an event to you to your streaming application, and then you'll have an updated view of the data, and then you won't have this problem of restarting the query. This works for some of the cases, but stream-to-stream joins have some limitations. Like, for example, you can only do stream-to-stream joins using equality operators. You cannot do non-equal stream-to-stream joins. So in this case, what I'm trying to do is, like if you look at this query, I'm trying to do a not in query, and this will not work for stream-to-stream join. Stream-to-stream join is fine for where you have equal queries, like if you're loading a reference table. Okay, and yeah, so this basically, these are the problems with getting data from traditional data sources. Another problem is writing data to traditional data stores like JDBC. Like if you look at the batch, in batch mode, Spark supports writing to JDBC, but this is something that is missing in streaming. In streaming, there is no JDBC sync. And actually, I implemented our own JDBC sync, and if you want, you can go and look at this GitHub, and that has an implementation of a JDBC sync, and this is something which we are using at Capital One. So this works just like any other syncs. Basically, when you want to write to JDBC, you say spark.write.format JDBC, and as long as you have the sync in your class path, you will be able to write to JDBC. Internally, it uses the same code as your batch JDBC sync, so it should give you the same performance. It supports overwrite and append modes, and it supports at least once and also exactly once. But to support exactly once, you need to configure it. Basically, you need to add a column into your table which stores the batch ID. And what it does is when it's repeating a batch, it will go and delete the old data and reinsert all the data again. And that's how it supports exactly once. So next family of problems that we ran into was with checkpoints. And what checkpoints is structured streaming stores the state of the streaming application in checkpoints. And why it needs it is to do recovery from failure. So what happens is when if your application fails, as the application is running, it keeps data in the checkpoints. Like it keeps offsets within the checkpoints. And when your application starts again, it loads data back from, it loads those offsets back from the checkpoint and then starts off from where it left off. So checkpoint is an important thing for structured streaming applications. You should have checkpoints enabled. The problem that we ran into is, what we realized is, and this was not completely clear to us when we started, for checkpoint, a checkpoint that has to be stored on some sort of file system. The file system has to be resilient to failure. I mean, that's obvious. If your Spark application dies, your checkpoint should still be there. It should not disappear, right? And also another important thing is that the checkpoint has to be shared between all the executors and drivers. So these two things we were familiar with. So we thought, okay, great, we can use S3 to store our checkpoints. What we didn't realize is that the checkpoint has to be immediately consistent. Because what happens is Spark between microbatches, end of the microbatch it writes to the checkpoint, and the start of the next microbatch it reads back from the checkpoint. And if your checkpoint location is not immediately consistent, what it reads back might be an old copy, and then your application will crash. And S3 is not immediately consistent, right? So this was a problem. We realized it a little too late, like right when we were going into production. We realized this because you don't see this problem unless you run it at scale. Right when we are doing a performance test, we started running into this problem. If you're running with a small amount of data, you'll never run into this problem. And what we saw is that it was like crashing after running it for 4 or 5 hours. So the solution is to use NFS. NFS is immediately consistent. What we ended up using is EFS. We are on AWS, so we ended up using EFS, which is AWS's version of NFS. We are also looking at Kubernetes. So if you are on Kubernetes, you need to use some sort of persistent volume that supports read, write, shared. And you will use NFS for cluster FS. But we haven't really tested it on Kubernetes well. These are some of the options we are exploring. Also, another problem we ran into with checkpoint is this bug, which was in 2.2. This bug is in state store, and state store is basically the part of the checkpoint that stores aggregations. So what happens is, if you're doing aggregations within your structured streaming application, Spark needs to store intermediate data about the aggregations into the checkpoint. So in case of failure, it can read it back and start doing the aggregations again. But there was a bug in Spark, and it will basically lose the checkpoint will become corrupt. And what we saw is that we didn't have too much load. We had an average load of 10 TPS, but it would peak at 300 TPS. And what we saw is that the checkpoint will get corrupt once a day. And we had to basically delete the checkpoint and restart the application, which means that we lost data while we were restarting the application. So luckily this was fixed in 2.1, and once we went into 2.1, this problem went away basically. And lastly, the third set of problems we had was with aggregations. So Spark does allow you to run any kind of SQL queries on your data frame, which is populated through streaming sources. It's called a streaming data frame. and you can run any kind of Spark SQL queries. But and so as part, you can run like aggregation queries on your Spark SQL statements on your streaming data frames. But you cannot aggregate an aggregated table if you're using structured streaming. It limits what you can do. And if people are familiar with people who are familiar with SQL, the way they partition their problem, like if they have a complicated problem, they tend to break the problem down into steps and write multiple SQLs. But the problem is that this does not work with Spark. If you have like a complicated problem, you'll have to write one big giant SQL. You cannot break your solution into steps. Another problem is partition by. This is like, people who are good with SQL know what partition by is. Do people understand what is a partition by? You do, yeah. What partition by is basically, it allows you to do aggregations, but push down an aggregation to row level. So for example, if you have like your salaries database, right, and you have people's monthly salary, right, what you want to calculate, let's say you want to find out how much percentage of the salary they got in November, let's say, right. You could, like, if you want to find what is the percentage of the salary they are earning each month, right, what you can do is you can aggregate all the salaries over time, but you want to put the aggregated salary at each row level, so you can calculate a percentage. Right? You could do this as two different operations, which doesn't work in Spark, or you can do it one partition by, using one partition by clause with just one SQL. The problem is internally Spark implements partition by clauses using windowing, and in structured streaming, windowing can only be done for time-based windows, not for non-time-based windows. So if you're doing a partition by on a field which is not time-based, Spark will complain and then won't let you move forward. So this was something which was blocking us. We wanted to use both of these things. What we ended up doing is doing our aggregations in Scala rather than using Spark SQL. What we did is we basically used this group by and flat map groups. And what this lets you do is get all the rows that are grouped by a certain field into a closure, and then you can do all your aggregations within Scala. And we ended up doing that. You could do if possible, you can pre-aggregate your batch data before you join it to your stream. That might solve some of the problems, but at least for us, it was not. That was not useful. But if you can do that, you should do that. So basically, that's it for the problems. We have some time for questions.
Thank you for sharing your pitfalls. And any questions you guys have? We have about 6 minutes. So, and I know you guys are dying for coffee break, but we can stay and talk about pitfalls and structured streaming if you want. Anybody?
Regarding streaming to stream, non-streaming to streaming for join, do you still get filter push down in that case?
When you're doing join, there won't be any filter push down on the join. But if you have any other filters, if you're just using a normal filter, that will get pushed down to the batch source.
So Spark can figure out that the stream source is actually a batch source that's been converted, and it will do the filter push down?
So what we had tried is doing filtering on the batch source before joining it with the streaming source.
Oh, I see.
I've never tried out doing a filter after the join.
Okay.
It's something to try out.
Such a question. Do you know if any of these shortcomings were addressed in Spark 2.3?
Sorry, can you repeat that?
Do you know if any of these shortcomings were addressed in Spark 2.3?
Sorry.
Shortcomings that you
So 2.3 adds stream-to-stream joins, which is really great. We are waiting for that. But stream-to-stream joins only on equality operators. So you cannot do a not in query. You cannot do a less than join, greater than join. You can do an equal to join. right? And also on the output mode, you can support, I think, only append but not update and overwrite modes.
Hi. So in the context of the second problem that you mentioned about the static data set joining to the real-time stream, and the problem of the static data set getting updated. So today we actually use the dstream API, the old API, and the way we solve that problem is by notifying from the static data source when it changes to the stream, to the streaming engine, and rereading that and recreating the RDD, right, in the dstream API. So is there a similar solution possible? We are thinking of actually moving to the structured streaming, but looking at these pitfalls, I think that stands out to me, would be one of the things that I would need to tackle differently, I guess. Do you have any suggestions?
So your solution is on Spark streaming and you're thinking of going to structured streaming,
Yes.
right?
Yeah.
So you could do like the code sample I showed where you're restarting a query. When it's time to refresh, you're sending a notification and basically set a flag, and when the flag is through, you go and restart the query.
Right, I saw that. However, the way we solve that today, the dstream API is pretty much more elegant. It just recreates the RDD and then continues. No need to restart anything.
Yeah, there's more options.
Okay.
In
Nothing
structured
similar to
streaming,
that.
there's no
Okay.
option.
Thank you.
Anybody else?
Good talk. Thank you very much.
Thank you.
I'm wondering if you guys have an interesting strategy for dealing with error cases and kind of debugging in structured streaming. So you have your input that turns into a data frame, and maybe a row is not as per your schema or unusual. Given that there's only one output for structured streaming, what are you doing? How are you capturing those errors?
Sorry, excuse me. So there's a similar kind of limitation for both batch and streaming. What Spark expects you to do is pre-validations. So as soon as you get your data, you should validate your data. Like Spark is not good in handling the error on the right side. Like, excuse me. So something fails, the Spark job will fail. There's no way to intercept exceptions when you write it. And the only way to do that is to do pre-validations. So basically we have built libraries that can do data quality checks before you even process, as soon as you get your data. Right, yeah.
Yeah, there is a callback function you can actually use. We actually have time only for one more question, but if you actually wanted to have more questions, Jayesh can probably answer a question during the break. And at the office hours at the Databricks booth, we'll actually have TD, who is the committer for structured streaming. You can ask any of those questions over there as well. Ready for the last question?
Hi. This question is not related to streaming, but did you encounter any issue for Cartesian product cross-join?
We haven't tried cross joins. Yeah.
All right.
I mean, it's not, usually you should avoid it.
Okay, well, thanks a lot for coming. Give a big hand to Jayesh for that wonderful, insightful talk.